All right, for this lesson, we're going to talk about absolute value. Absolute value of those bars that you're seeing right here on either side of X. You can put letters in there, numbers in there. We can create equations, whatever we need to. We're going to look at some examples here in a second. What it is ultimately is a magnitude. It's a distance from zero. In fact, let's go take a look right now. Let's say we had the absolute value is how you describe it when it has the bars around the number, the absolute value of 7. The idea is we're going to put things inside the bars, and whatever comes out, the answer is going to be positive. So if you put a positive 7 in here, the absolute value of positive 7 is still positive 7. Let's say we took negative 4. This time the negative number goes in, but what's going to come out? Well, the bars are going to make it positive. This is a distance, so it should never be negative. Think about that. Let's look at this number line. So here's 0 in the number line. Let me grab my pen. And what we're saying is this guy went to negative 4, so negative 1, negative 2, negative 3, negative 4. It's right about there, but still went a total of 4 units or 4 steps, which would be the same. Let's say it was positive 4. 1, 2, 3, 4. There's positive 4, but the same number of units, 4 units. So we're trying to measure how far away from 0 are you. Works the same way with 7 and negative 7. So the idea is whatever goes in here, positive or negative, doesn't matter. It's going to come out positive. Now, what if there's something else out here? See, this negative right there is not inside the bars, so it gets to play by its own rules. This will not turn into a positive because it's not on the inside of the bars, it's on the outside. So the idea is the 9 is inside, it will come out positive, but then this negative is outside and it's going to get a hold of it the second it comes out. And that's why this guy is negative 9. So if there's something outside, it's going to win. Ultimately, that's going to be the sign. Here's another way to think about it in terms of distance. I watched a video and this lady talked about running, and she said it doesn't matter where I run or how I run, I'd never run a negative distance. And I thought, well, maybe this is what she was talking about. Let's say we're runners, and let me erase some of the writing I've done here. Let's say this is the starting line right here at 0. And you know how people go down, they get in their little stance, getting ready to run and take off. And usually somebody fires a gun, right? And that's the start of the race. And so most of the runners take off and they start running like they're supposed to. Well, let's say we got this new runner. They've never run an official race before. They hear the gun and they're like, oh my gosh, there's a gun. Somebody's got a gun. Everybody run. And this guy runs that way. Well, what if they made it to here? And then everybody else made it to here. And then at that point, somebody gets on the PA system and they're like, listen, everybody, we're sorry to startle you with this gun. That's normally how we start the race. Let's all line up again. In this moment that the PA guy stops everybody, these runners are here. How far did they go? They went 1, 2, 3, 4. They're 5 meters in the correct direction. The scared runners, 1, 2, 3, 4, still 5 meters, just not on the track, not where they were supposed to run, but they're the same distance from 0. Both of them are positive. This guy didn't run a negative distance just because he was scared and went somewhere else. That's one way to think about it. I don't know if that's the best example, but take a second, write all this out, pause the video if you have to. We're going to fill this in. This is talking about the absolute value parent function. So now we're looking at equations and functions. We're going to throw some letters in there. X is inside, so I'm assuming whatever comes out is going to be positive. We're going to look at that in the table here, draw a picture of it. After we look at the graph of this, we're going to go look at some things, some key attributes. We've done domain and range before. We're going to add to it today. We're going to do x-intercepts, y-intercepts. You've probably done that in Algebra 1, and then we're going to add to it some Algebra 2 stuff. What is the vertex? What is the axis of symmetry? Let's go do that now. I'm going to head over to Desmos. I'm going to see if we can't draw a picture of this thing. move my stuff around. In Desmos, you can type y equals, or I like to do f sub 1 of x equals. Either one's going to give it the same thing. You're going to find that in this little keypad in the bottom left is where the absolute value bars are. See A inside the absolute value. Kind of gives me the ghost bar and the real bar. I'm going to put an X in there. That's the parent function. Look at that. It's a V shape. Goes right through the center of the graph at 0, 0. That's called the origin. I'm going to hit the right arrow key and then the space bar, and now it's no longer a ghost. The second bar pops up. So there's our absolute value parent function. Now going back to what they asked me to do here, I've already got my picture, so I can start drawing that if I want to. Kind of did something like that, right? We're going to find out in a second it's going to go on forever, so I'm going to draw some arrows at the end of this to show that it goes on forever. Now notice our table is blank here. If that's the case, here's what I suggest. I've got go-to numbers that I like to use, not just for the absolute value functions, but for really any function. Algebra 1, 2, 3, 4. Does algebra go that high? I don't know. What I like to do is use the values -3. Whoops, where'd the negative go? And then I like to use -2, -1, 0, 1. That's not a 1. 2. Let's see if I can line these numbers up a little better. There we go. Oop, I forgot -1, didn't I? Stretch this guy out. Put 0 there. Okay, I think everybody's where they belong. And let's add a 3 at the end. Let's go -3 all the way to +3. Now, here's why I like these numbers. I like them because they're small numbers. And that means the math is going to be easy. If I said to you, hey, use 0, what's 2 times 0? Immediately you would know it's 0. If I said, hey, what's 5 plus 2 minus 4? 5 plus 2 is 7, minus 4 is 3. You'd be able to do that without writing it down. So that's why I like these numbers. Even the negative ones, oh, I see what I did here. I put 2 -2s. Let's get rid of one of those. Even the negative numbers are pretty small. 2 times -1, that's -2. That's easy to do as well. Here's the other reason I like it, because it's giving me the fuller picture of what's going on. I know some of you don't like to use negative numbers, but if you didn't use negative numbers, here's what you'd see on the graph. You only see the right side, right, where all the positives are, and you'd think this was linear. You'd think it was a straight line, but it's not. So the negatives help us kind of see the fuller picture that, yes, this is a V shape. There's some stuff happening over here where the negative values are as well. All right, so let's go ahead and get a table for those values. I'm going to tweak this a little bit. We've got an X. It's got to match everything up at the top in my equation. So f sub 1 of X. And now we said we're going to use the values -3, -2, -1. Notice it's filling it in for me. That means I did it correctly. 1, 2, and 3. Let's take a look at this. If this is -3 as my input, why did +3 come out? When I put in -2, notice +2 came out. When I put in -1, +1. It's because of those bars, right? Those bars are turning everything into positive. All the outputs are positive. Even if you put in positive numbers, you're still getting out positive numbers. And that's what creates this V shape. You put in some negatives, but you're still getting the positives out. You put in some positives for X, and you're still getting positives out. So everything should be in the positive Y section. All right, so we know the values now are 3, 2, 1, 0, 1, 2, 3. Let's go fill that in real quick. 3, 2, 1, 0, 1, 2, 3. Stretch it out, make sure it's in the table. You have to space it a little better. There we go. So you don't have to use these numbers. These are my recommended numbers. That's what I like to do. Use small numbers, couple positive, couple negative. So now let's get the domain and range. We're looking at this. We drew it. Remember, tell your brain domain is left or right. If we trace this to the left, so we're heading to the negative numbers, we want to look at the x-axis. Where will it stop? Well, it turns out, because we drew arrows on here, it's not going to stop. It's actually going to go to negative infinity. What about to the right? So tell your brain we're going to the right. We're still looking at the x values. Those are positive in that direction. It's not going to stop in that one either. If you went to Desmos and dragged it, look what's going to happen. Yeah, that red line just keeps on going. It's never going to stop. So when it goes off the screen or it has arrows, you get to assume that it's going forever. If that's the case, what we're going to put in here is negative infinity to positive infinity, or another way to do it is just call it all real numbers. So is the range all real numbers too? Remember, the range is up and down. So now we're looking at the y-axis. If I traveled this line, or let's even go over to Desmos. That's a cooler picture than the one I drew. What if we go down this red line? Does this red line go down forever? No, I don't see anything down here. Remember, we said it had to stay up here in the positive y's. So how low did it go? Looks to me like it stopped right here. Looking at the y-axis, what value is right there? Well, I see 0. So then if I travel up, tell your brain you're going up and down. This is the range. If I go up, it doesn't matter if I go up on this one or if I go up on this one. I'm trying to find the highest point in the graph. And again, it goes off the screen. If I drag this thing up, look, that red line just goes up forever. So we're going to say this goes to infinity. We said for the range, we're going to use a bracket for this one. The range went as low as 0, that's included, that's a point on our graph, but then it went all the way up to infinity. You can do the symbol, or you could just write positive infinity. That's not a place we can touch on the graph, so we're going to use parentheses for that one. All right, x and y intercept, that's where does my v touch the x-axis? Where does it touch the y-axis? So let's look at the x-axis first. That's right here. Looks to me on the x-axis, we're touching right there. What value is that? That is 0. Let's go confirm it. The coordinates are 0, 0. Okay, let's go type that in. Zero, comma. Move all these up. I'm going to fix that parentheses. Delete that one. Okay, looking at the y-axis and the v, where did those two touch? Here's the y-axis, here's my v. The y-intercept then would also be 0, 0. It's touching the x and the y in the same place. That's not always the case, but in this case it is. So we're going to say the y-intercept is also 0, 0. Vertex, that might be a new one for you. Now the vertex, let me go get a highlighter here. We'll do the pin first. The vertex, turns out it's the same point. It's where it stops going down and starts rising again, stops decreasing and starts increasing. It's the point of the V. That is called the vertex. And if we went over, got the coordinates again, you're going to see it's 0, 0. For this parent function, a lot of stuff is 0, 0, and that's okay. We'll see some new numbers with new functions later. The vertex is 0, 0. That's the point of the V. Now, this first value right here, that is called the AOS. That's the axis of symmetry. I like to shorten it and just call it the AOS. We only want the first value. The first value is the x value, right? So for the axis of symmetry, we're saying x is equal to 0. The axis of symmetry, it's kind of like the line of reflection. See, it folds right through the vertex at x equals 0. And this side of the graph would match perfectly this side of the graph. It's kind of like a heart, right? If we folded a heart, it would line up perfectly when we fold it. And that's what we want with these V's. So where you fold it, that is the axis of symmetry. All right, we found all the key attributes is what they call these. Let's look at another graph. Now I want to point out this one has the table already filled in. It's got some of my go-to numbers, not all of them. In fact, it goes a little bigger. It goes up to 4. Now I didn't give you these values. These were pre-filled in. So what that tells me is whoever wrote this says I have to use these numbers. In this previous graph, that wasn't the case. This table was empty. I got to do any numbers I wanted, and I chose my go-to numbers. I'm the one who chose, but in this graph, somebody else chose for me. When that happens, that means we can't use arrows on the graph. Notice I stopped at the parameters they gave me. They said you need to stop at -3 and you need to stop at +4, and that's what I did. There's -3 and there's +4. I got to include all the numbers in between, of course. So it started here and stopped here. That's going to affect the domain and range. When I get to choose the numbers for the domain and range, notice I've got some infinities. I've got all real numbers. I've got arrows. Things go on forever. But when somebody tells me I have to stop, well, then I have to change how my domain and range looks. This one says do interval notation. The domain stopped at -3, or I should say started. That's included in the table and on the graph, so I'm using brackets here. Then it went all the way up to +4, so no infinities in this one. Had a starting point and a stopping point. The range, kind of similar. How low did this thing go? Now, some people want to look at the top number in the table and the bottom number. You cannot do that. Some people write things like, hey, this started at 3 and it ended at 4. No, it didn't. It didn't do that. You have to look at the lowest. Remember, this is smallest to biggest. So what is the smallest value in this table? What is the biggest? Well, digging through here, it looks to me like 0 was the smallest value. What's the biggest? 4 was the biggest. So this is 0 all the way up to 4. So be careful with that. If we did the same thing, but this time in set builder notation, we would just take this -3 and +4, split them up. Arrows go to the left. These are both included because of the brackets. Everything's solid here, no holes. So we're going to put lines under the arrows, and domain is the X value. For the range, Y, arrows go left, lines underneath, and we said those values were 0 and 4. So they tell you which numbers you have to use. Those are parameters. Those are restrictions. Here's the way that normally looks. Domain restrictions is the name of it. They're saying you got to start at 2 and you got to end at 7. And notice this is written in interval notation. So the domain for this one would be 2 all the way up to 7. And then I would have to go use Desmos to figure out the rest of my key attributes here. Let me look at my next slide. Yeah, we'll go ahead and end it here. I'm going to fill some of this out. This is absolute value of X minus 4. So look what we can do here. We can just go ahead and update this. There's the -4. I don't have to erase everything. It's going to fix my graph for me. It shifted it over. It's no longer in the middle here. They tell me the values that I have to use are 2 all the way up to 7. Get rid of this one. And now the table updated as well. So let's go update our table 210, 1, 2, 3. Ours is 210, 1, 2, 3. And they wanted us to use, whoa, that's not a 2, 2, 3, 4, 5, 6, and 7. Okay, so the range then will include, remember, we're looking for the lowest number. It looks like it's 0. And then the biggest number here is 3. So we had a range from 0 to 3 in our graph. The vertex, where was the vertex in this one? The vertex is that V. If I click on the coordinates here, looks like it's 4, 0. Oh, notice that's also the x-intercept because it's on the x-axis. So the vertex and the x-intercept are the same. Let's go fill those in. The vertex is at 4, 0. Same for the x-intercept, 4, 0. Remember what the first value was of the vertex? This guy right here. That was the AOS. It's not changing colors for me. This guy right there, that's the axis of symmetry. Because it's the x value, its x is equal to 4. Let's go see what the y-intercept is. Where does this v touch the y-axis? Looks like it's right there. What are the coordinates for that point? 0, 4. There we go. We're not going to talk max and min just yet today. We'll do that in the next lesson. What is the parent function? The parent function is f of x is equal to the absolute value of x. That's the first one we did today, right? So the idea is the parent function lives in the middle. That's a horrible representation, but you get the idea. Go back and look at your graph from earlier. And then the graphs shift as we start to add numbers to them. The parent function doesn't have any values, which is why he's stuck in the middle. But this guy does. He's got that -4 now in there, which moved him over here. So here's the parent. Here's the new one. Or when they ask you, you're probably just going to write it like that.